The galaxy has had 13 billion years and 200 billion stars to produce another civilization. We have found exactly zero. Not one signal, not one probe, not one trace. And that silence may be the most ominous fact in all of science. In 1950, during a lunch at Los Alamos, the physicist Enrico Fermi crystallized the problem in a single question. He had just calculated how many civilizations should exist in our galaxy. The number was large. He looked up at his colleagues and asked, "Where is everybody?" 75 years later, the question still has no clean answer. The setup is simple. The Milky Way contains roughly 200 billion stars. A large fraction of those have planetary systems. We know this now from the Kepler mission, which surveyed a small patch of sky for transiting planets and concluded that planets are essentially universal. A significant fraction of those planets are in the habitable zone of their host star, where liquid water is geometrically possible. The galaxy is 13 billion years old. Earth is 4.5 billion years old. Earth-like planets older than our Sun exist in great numbers. Many of them would have been candidates for life billions of years before Earth was. If even 1 in a million of those older habitable worlds produced a technological civilization, and if even 1 in 1,000 of those civilizations spread beyond their home star, using probes, automated mining, or directed signaling, the galaxy should contain detectable evidence of them. Detectable does not mean visible to the naked eye. It means catchable by deliberate radio scans tuned to natural transmission windows, by optical pulse searches looking for laser communication, by infrared surveys looking for the waste heat of large-scale energy use. All 3 of these search programs have been operating for decades. The most recent, Breakthrough Listen, funded in 2015 and using major radio observatories worldwide, has been scanning targeted stars and the galactic plane for 10 years. The result has been silence. A few unexplained anomalies, all of which have ultimately been attributed to natural sources, terrestrial interference, or instrumental noise. No persistent narrowband signal, no coordinated optical pulse, no infrared anomaly consistent with a Dyson swarm. This is the Fermi paradox. The math says the sky should be loud. The data says it is quiet.
In 1961, the radio astronomer Frank Drake organized a small meeting at the Green Bank Observatory in West Virginia with the goal of formalizing the variables involved in answering Fermi's question. The result was an equation, not a precise formula in the physics sense. Too many of its variables were unknown, but a framework for organizing what would have to be true for the galaxy to be quiet. The Drake equation multiplies together the rate of star formation in the galaxy, the fraction of stars with planets, the number of habitable planets per such system, the fraction of those that develop life, the fraction of those that develop intelligent life, the fraction of intelligent species that produce detectable technology, the length of time those technological civilizations remain detectable. The product gives the number of currently detectable civilizations in the Milky Way. When Drake first wrote the equation in 1961, every variable beyond the first 2 was a guess. In the 65 years since, the first 3 variables have been measured with reasonable precision. Star formation rate? Known. Fraction of stars with planets? Essentially all of them. Habitable planet count? About 1 in 5 Sun-like stars has at least one habitable zone candidate. These numbers are large.
The middle variables, the biological steps from chemistry to life, from single-cell life to multicellular, from multicellular to intelligence, remain completely uncalibrated. We have one data point, Earth. We do not know if life arose easily here or with extraordinary improbability. We do not know whether intelligence is a generic outcome or a one-time accident. The last variable, civilization lifetime, is where Fermi's question becomes uncomfortable. If technological civilizations typically last only a few centuries before either destroying themselves, contracting back to non-detectability, or transitioning to a phase we have not anticipated, the silence is explained. The galaxy could be full of civilizations, rising and falling on million-year cycles, each detectable for only a few hundred years, and we would never overlap with any of them. But that explanation requires the civilizations themselves to be common, and the silence to be a sampling problem. Drake's framework allows it. It does not require it.
In 1998, the economist Robin Hanson published an essay called The Great Filter. Are we almost past it? His argument was structural. The chain of necessary steps from inert matter to a galactic-scale visible civilization can be enumerated. Chemistry, abiogenesis, single-celled life, multicellular life, intelligence, technology, interstellar capability. Each step has a probability of happening. The product of those probabilities times the number of starting candidates in the galaxy equals the expected number of visible civilizations. The observation that the galaxy is empty means the product is small. That, in turn, means at least one of those steps must have an extremely low probability. Somewhere in the chain, there is a filter, a step where most candidates fail. The great filter is the bottleneck. The question is which step it sits on. Hanson's framing is that the filter must be either behind us or ahead of us. If behind us, then one of the steps we have already passed, perhaps abiogenesis, perhaps the origin of complex cells, perhaps something about intelligence itself, is the rare event that explains the silence. In that case, we are extraordinarily lucky. We have already crossed the wall that almost no one else crosses. The galaxy is quiet because there are very few civilizations like us, and we are among the few. If ahead of us, the implications are darker. The filter is something we have not yet faced. It could be self-destruction through technology, nuclear war, biological catastrophe, runaway artificial intelligence. It could be a natural disaster on long timescales, supernova nearby, gamma-ray burst, false vacuum decay. It could be a behavioral limit. Civilizations that develop sufficient capability tend to reorganize themselves in ways that make them invisible, intentionally or not. The 1998 essay was clear. We want the filter to be behind us. If it is ahead, our probability of crossing it is, by the same argument, very low. The reason this matters more now than in 1998 is that the first variables of the Drake equation have moved upward. We thought in the 1990s that planets might be rare around other stars. We now know they are nearly universal. We thought habitable zones might be uncommon. We now know they exist around a large fraction of stars. Each upward revision of the early variables pushes the burden of the silence onto the later steps, the biological and behavioral ones, and makes the filter likelier to be in those steps. If the filter is in abiogenesis, the discovery of any independent biosignature on Mars, Europa, or Enceladus would be catastrophic news. It would mean life is easy. The silence would then have to be explained by a step further down the chain, a step we have already passed, like the rise of intelligence, or a step ahead of us. The mere detection of a second instance of life in our solar system would push the filter forward. This is the unresolved tension. Every new exoplanet survey, every astrobiology mission, every step toward detecting life elsewhere is, paradoxically, a step toward either great relief
or great concern. Relief if life turns out to be rare and we have already crossed the filter. Concern if life turns out to be common and the silence demands a different explanation. The honest answer in 2025 is that we do not know which it is. The silence is real. The framework for interpreting it is well developed. The data needed to discriminate between the two possibilities, most importantly, the detection or non-detection of life elsewhere in our solar system and on the nearest exoplanets, is the central project of astrobiology for the next several decades.
Next video. There is a final, slow-motion end the universe is moving toward, predicted with high confidence by physics. It is not a bang. It is not a collapse. It is a 100 trillion-year drift into permanent silence. The technical term is heat death.